Every day, thousands of thunderstorms are active across the surface of the Earth. Mysterious and spectacular phenomena have been observed above the thunderstorm clouds. Made in the 90s, these discoveries show that the thunderstorms affect not only the lower layer of the atmosphere, but also the upper layers up to the near-space environment. What we need to do now is discover and understand the hidden side of thunderstorms. Taranis, discovering the hidden side of thunderstorms. Observing luminous phenomena above thunderstorms is not easy, as it has to be done from afar using specifically adapted instruments. The phenomena produced by the thunderstorms are so brief that they cannot be easily detected by the human eye. These phenomena are grouped together under the generic term of transient luminous events, or TLEs. The first TLEs that have been observed are the sprites. They occur at an altitude of between 40 and 90 km, display a complex filament structure, and can be accompanied by a halo or not. A sprite lasts for a few milliseconds. The elves are the highest, the most frequent, and also the briefest of the TLEs. They typically last for 1 millisecond. They occur at an altitude of about 100 km and appear as a rapidly expanding ring of light. The rarest TLEs are the jets. The jets may last up to a few hundred milliseconds. The blue jets project from just above the clouds and propagate to an altitude of 40 to 50 km. On occasions, a jet might reach an altitude of 80 to 90 km, when it is then referred to as a gigantic jet. Observation from space is particularly well suited to studying the hidden side of thunderstorms. The Taranis satellite is therefore dedicated to the study of these luminous phenomena. The mission of the MCP instrument, composed of a group of 4 photometers and 2 microcameras, is to detect, characterize, and systematically localize all the TLEs flown over by the satellite. Apart from the TLEs, the storms give rise to another type of fascinating phenomenon called terrestrial gamma ray flashes, or TGFs. In certain conditions, the storm acts like a particle accelerator. During this process, highly accelerated electrons generate an ultra-short burst of gamma photons of less than a millisecond. Taranis also studies these gamma photon emissions. Installed on board the satellite, the XGRE instrument is an ultra-fast scintillation detector, being used for the first time in space. Highly energized runaway electrons would automatically be associated with a TGF. While the photons propagate upwards in a straight line, the electrons travel along the Earth's magnetic field lines. The IDEE instrument identifies these high-energy electrons. Thanks to these detectors, it can distinguish the electrons associated with the TGFs from electrons from the upper atmosphere. When a beam is intercepted, the instrument measures the energy of the electrons and shows where they have come from. TLEs and TGFs are expected to be accompanied by bursts of electromagnetic waves carrying very valuable information about the origin of these phenomena. On board Taranis, wave measurements are performed by a suite of 3 distinct experiments to cover the frequencies ranging from DC up to a few tens of megahertz. 2 instruments are devoted to the electric and magnetic field characterization for the low-frequency part of the waves, up to 1 MHz. The instrument IMM, which is composed of the 3-axis magnetic antenna to measure the 3 magnetic field components, and the instrument IME-BF, equipped with an 8-meter dipolar antenna to measure 1 electric field component. To complement the system, the high-frequency part of the electric field measurements is performed by the IME-HF instrument, which covers the frequencies ranging from 100 kHz up to 35 MHz. Taranis is the first space mission with the capability to identify simultaneously the optical X-gamma electron beam and electromagnetic signatures associated with the transient luminous events and terrestrial gamma ray flashes. A mission in search of the hidden side of thunderstorms.